alloy steel. We used a water jet to cut out the flat plate pieces. And then for the center hub section, we turned that on a lathe and we inserted another grease seal in the bottom of that. And then for the pipe coping right here, we constructed a wooden jig that would hold it, so we could do that with a drill press and a hole saw, and that's how we coped the pipes. Once we had the base of the frame completed, then we used a hydraulic tubing bender to get the handlebars you can see in the back of the chair. And then we just had it MIG welded together and had the entire frame powder coated. For our height adjustment mechanism, we elected to purchase the gears, the chain, and the chain guard. And then using the lathe, we manufactured the shafts with the bearing surfaces on them and the gear adapters that adapt the sprocketed gears to the base of them that allow them to be bolted on. And then we used a bandsaw and hand grinder to grind these flat metal shapes you see here. And then we just welded and bolted the various components together. For our angle adjustment mechanism, it has a HOM joint located here and a pillow block bearing here that we purchased. And then once again, for the threaded components, we used the lathe to manufacture these, then welded them together at the weld joints, and then used a hand grinder and a bandsaw to manufacture the handle flat piece right there. For our foot supports, we used the water jet to cut the flat plate, and it was A36 mild steel, 1/4 inch thick. And then we made some modifications with the bandsaw to cut some of the links down after they were modified. And then we used the milling machine to cut these grooves out for the adjustment. And then we just welded the flat plate components together. And for the actual adjustment, we used 5/16" bolts to allow this to telescope up and down, and for the foot pads to come in and out to vary the width. We elected just to purchase the caster wheels because it's far cheaper than trying to manufacture them. And in the back, the only component that we required was a 5/8" solid steel pipe. And we just cut that to length using the bandsaw and then welded it onto the brake tabs.
Hi, I'm Arthur Hebert. Here are some of our conditions we used in our analysis. Generally, we design a chair for a 150-pound patient, and we designed it for some of the cases to withstand 100-pound horizontal loads, and in other situations, 150-pound horizontal loads. It should be noted that when the patient gets in the chair, the therapist usually will load the patient into it, and therefore the therapist could step onto the frame with the patient, and it would be a combination of the combined weight on the wheelchair. Also, this last bullet was just assumed for our dynamic model that all 4 wheels were in contact with the ground. In this model, when we were designing the frame, to meet the static conditions, very small tubing was required, but it was clear that just dropping something onto the center of it would cause a small tubing to deform. So we did a situation where a mass is dropped from 12 inches, that's 150 pounds, into the center of the seat. And this blue curve is the displacement of the seat relative to the ground, and it displaces about 4 inches. And this green curve is this curve down here. And the top of the frame relative to the ground displaces about 4 millimeters, but that's with the springiness of the wheels. From this, we iterated, and from that, we decided what tube size to pick, and we came out with 1 5/8 tubing to be able to withstand something dropping from that high. For the retainer, for 150-pound force, applied 48 inches from above the bottom, then the jack screw kind of acts as a crowbar, and this force acts on the retainer that holds the jack screw down, and the retainer has 2 forces to counteract it. And it's a symmetrical situation, so you only have to do one case. And this force stops the prying action, and the bolt that holds it down has a stress less than 10,000 psi, and that gives you a safety factor of about 3. And another situation is that the jack screw essentially is a cantilever beam, and the bending stress at the base of it is less than 7,500 psi, which is also well within limits. Since it gets loaded more than once, it is low cycle, but we decided to check it out quickly. And usually an equation from Shigley's Mechanical Engineering Design, we use some of the factors and the endurance limit, and then we found the fatigue strength of the bolts, and it came out to be 25,000 psi, which is a good deal above 7,000 psi. And so it is a simplified model because the bolts are in shear as well, but the shear and stress is low. And also, but we thought the simplified model was sufficient because it was designed for the worst case scenario. The cycles are low, and bolt preload would only make the situation better. For the there's quite a few loads in our chair. We chose to show this one in our presentation today. And this one, on many of the loads, we just welded it all the way across, so it essentially just connects two pieces of metal completely. But on the seat, we only did 4 1-inch welds versus like 4 3-inch welds, which is the width of the hinge right there. So, and we chose to just do 4 1-inch welds because each hinge does not experience the bending moment itself. The two hinges together can provide reaction forces for forces acting on the seat. So for a 150-pound force applied somewhere away from the seat, like on the seat back here, or vertical, or up here, if it's 24 inches away and it's 150 pounds, the stress level in the weld is less than 7,500 psi, which is which shows it won't yield. For our foot supports, we were planning to machine grooves, triangular grooves into the sides of them, so that it was mechanically connected when someone stood on them. But we decided just to check how much friction was between them. And in this case, we used a 264 vertical pound force acting on 1 foot support. And for this, if the friction factor was assumed to be 0.4 for the steel against the steel, the normal force would have to be 660 pounds. And to obtain this, the axial force in the bolt, which has a friction factor as well. In this case, we just assumed 0.08, but if it was doubled, the torque required would double as well. But so the torque required to obtain the axial load is only 13.6 pounds. And even if that was double, it's still easily obtainable with the tool we surprised, which has a 5-inch moment arm, which means the therapist only has to provide less than 10 pounds to achieve the proper torque.
My name's Adam Blessing. I'm going to be finishing up the testing that we accomplished. The assumptions that we wanted to incorporate at the very start of the testing was, first of all, maximum weight of both the patient and the chair, 300 pounds with a 150-pound patient at max. A level ground and floor deformation negligible, just like in the analysis that Arthur went through. And also we wanted to make sure that we maintained coherence with the ISO standards. There were 2 main aspects of testing overall, the first of which was from ISO and FDA, which there was some data that we were able to account for, but most of it was on a pass or fail basis. If the part was still intact after the test was over, then the test itself was accomplished it. And also we wanted to get direct feedback from McMains themselves, bring our completed model to them, let them test it out with the patients and see if it meets all of the standards that we had in mind. The first one that we had to accommodate was known as the tip-over testing from ISO. This is where we applied a maximum weight of 150 pounds at the fully raised height of the chair, and then tip it over both forward, backwards, and from left to right, and then measure those angles both measure the angles that occurred whenever the chair itself would tip over. Next, please. We also had to accommodate for the brake and traction testing. Now, for ISO, they said that you had to maintain at least brake safety at least on 112 slope, which is about 4.8 degrees. And to do that, it was the same thing with the tip over testing as well. They both were able to be accomplished at the same time, which I'm going to show the results of in the next slide, please. Now, like I said, the max height of the chair, this is between the top of the retainer and the bottom of the, top of the collar and the bottom of the retainer, was a total of 9.5 inches. That was as high as it could go. And we applied 150 pounds on the chair itself. For the chair tip direction for forward angles, the brakes started to slip at 11.72 degrees, and the chair itself tipped over at 30 degrees. Whenever it was angled backwards, there was at no point where the brake slipped. The way that the brake is set up is it digs itself into the wheel. And with it angled backwards, all that force just jams the brake on harder, as opposed to being forward where it starts to slip away. So it actually tipped over before it slipped at 28 degrees. And then for the left and right, excuse me, it started to slip at 12.3 degrees and tipped over at 17. Now for the tip over test, we just had to find the actual angles. For the brake test, we had to be, like I said, over 4.8, and in all cases, we were more than double that. So we passed those two tests. And here's just an example of the test that we've gone through. Max weight in the chair, 150 pounds, with it fully raised, on a platform that we slowly increased until it slipped or tipped over, and then we merely measured the angles that occurred in both cases. For the foot support testing, we had to make sure that it could withstand 150 pounds, the maximum load 150 pounds on each of the supports, as well as half of that going from the upper direction onto each individual foot supports. And the way we did that was we simply just put the weight in the chair, weight in the foot supports while they were fully lowered and also placed fully on, extended on right and left to make sure that it was on the worst case scenario. And for those tests, both individual foot supports, both individual foot supports were able to withstand the, as you can see, they were able to withstand the tested 150 pound max, and also, like I said earlier, they were fully extended whenever we did both of those tests. The next one that we had to do was the armrest test, which is to make sure that they could withstand the full, each of them individually as well as together could withstand the full load of 150 pounds. This to simulate the child getting in and out of the chair. Now for most of the kids that they have there, they have to have help getting into the chair, but we wanted to make sure that we accommodated for this just in case they had to support themselves in one way or the other. And we, with both armrests applied as well as individual, they were able to withstand 150 pounds with little to no. We weren't able to see any damage that could be observed from that test. And here's an example. This was whenever they were both being tested simultaneously, just with the full weight applied on a plywood across both armrests. And that's without any interference on us. It's still able to hold that weight. It's still. The next one is the caster wheel rolling impact test. And this is where we had to take the chair, load it with 150 pounds, and run it into a curve, both at 90 degrees and from the right and left at 45 degrees. And this is to simulate just an accidental collision that may have occurred at any point when using the chair. For the head-on collision, both of the casters remained intact with no damage. On the right side, from a 40-degree angle, the caster itself was okay, but as you can see, the metal bracket, we were able to repair it, but the metal bracket did not recover that impact. And also from the left side, this time the caster wheel itself was chipped. However, in both cases, the chair was still able to roll away, so it passed the test. And we were also glad to see that, mainly because we wanted the casters to fail before the frame. It's one, for safety reason, and two, it's much easier to replace the $20 wheel than it is the $1,000 frame. So the next was the torque impact input test, which was to measure the amount of torque necessary to both raise the chair up and down with no weight and full weight applied, as well as the amount of torque it took to adjust the chair's angle. For the first test, for the height adjustment test, there was no weight applied. It took 3.75 foot-pounds of torque. This was the amount of weight based on the length of the arm of the crank in the back. For the second test, with the full weight applied, it took 4.25 foot-pounds of torque. And also for the angle testament, regardless of the amount of weight that was applied,